The oceans, which have existed for nearly as long as Earth itself, are one of the most ancient and defining features of our planet. Formed around 3.8 billion years ago, they cover more than 70% of Earth's surface, making them the dominant feature of our planet's landscape. The oceans are not just vast bodies of water, they are also cradles of life and engines of climate regulation, playing a critical role in shaping Earth's environment and the development of life. But what lies beneath the waves, and how much do we truly know about this great unknown? Let's dive deep into the oceans, the lifeblood of our planet, responsible for creating and sustaining life on Earth. From their turbulent birth billions of years ago to their role in regulating the climate today, the oceans are not just bodies of water. They are powerful, ever-changing forces that shape our world in ways we're only beginning to understand. Picture this: Earth 4.6 billion years ago, a molten fiery ball spinning through space. No oceans, no clouds, just molten rock and volcanic eruptions. It's hard to imagine now, but there was a time when Earth had no water, and then something extraordinary happened. As the surface cooled, gases trapped deep within the planet, including water vapor, escaped into the atmosphere. Slowly, over millions of years, that vapor began to cool and condense, falling back to Earth as rain. Not for hours or days, but for millions of years. Imagine the sheer magnitude of that transformation. What began as molten rock was now becoming the oceans we know today. During this time, the oceans became the setting for one of the most significant events in Earth's history: the origin of life. Life is thought to have first emerged in the oceans around 3.5 billion years ago, when simple microorganisms evolved in the nutrient-rich waters. The ocean provided a relatively stable environment, protected from the harsh radiation of the sun and the volatile conditions on the early Earth. Early forms of life, including bacteria and archaea, were able to thrive near hydrothermal vents on the ocean floor, where they used chemical energy from the Earth's interior to fuel their survival through chemosynthesis. Over millions of years, life in the oceans became more complex, evolving from simple single-celled organisms into the vast diversity of marine species we see today. This evolution, spanning billions of years, created not only modern marine life but also ancient creatures that once dominated Earth's waters. But as life grew more complex, what creatures began to dominate the oceans? How did they evolve to survive the ever-changing tides of the planet's history? One of the most fascinating groups from this time were the ammonites, long-extinct cephalopods that thrived in the oceans during the Jurassic period, 200 to 145 million years ago, and the Cretaceous period, 145 to 66 million years ago. Ammonites, related to modern-day squids, octopuses and nautiluses, are instantly recognizable by their tightly coiled, spiraled shells. These remarkable creatures were incredibly diverse, evolving into a vast array of shapes, sizes and patterns. Over their lengthy reign in Earth's oceans, ammonites became one of the most prolific and widespread marine organisms, thriving in different marine environments. Much like their cephalopod relatives, ammonites were likely carnivorous, preying on smaller marine animals such as fish, crustaceans, and other mollusks. Their unique chambered shells gave them remarkable control over their buoyancy. By adjusting the gas and fluid levels within these chambers, ammonites could rise or sink in the water column, enabling them to hunt for food at varying depths. The diversity of ammonite shell shapes was immense, with some species featuring smooth, streamlined forms, while others had elaborate ridges and spines. These variations likely corresponded to the different habitats they occupied, from the open ocean to shallower coastal regions. The rapid evolution and wide distribution of ammonites have made them a key species for paleontologists who use ammonite fossils to date rock layers through a method called biostratigraphy. However, like many species that once dominated Earth's ancient seas, ammonites went extinct around 66 million years ago during the same mass extinction event that wiped out the non-avian dinosaurs. Their legacy, preserved in the fossil record, provides a snapshot of marine life during the Jurassic and Cretaceous periods, offering clues about the diverse ecosystems that existed in Earth's oceans long before humans. Today, the oceans continue to be the largest habitat on Earth, supporting an extraordinary range of life. Marine ecosystems span from the sunlit surface waters, teeming with fish, whales, coral reefs and plankton, to the dark, cold depths of the abyss, where strange bioluminescent creatures and deep-sea invertebrates thrive in extreme environments. The oceans are home to some of the smallest organisms on Earth, like phytoplankton, which form the base of the marine food chain, as well as the largest animals ever to have lived, such as the blue whale. This diversity of life is a reflection of the ocean's immense range of environmental conditions, from the warm tropical waters to the frigid polar seas, from the shallow coastal regions to the deepest ocean trenches. Each part of the ocean hosts species that are uniquely adapted to survive in those conditions. Coral reefs, for example, flourish in warm, shallow waters, creating vibrant ecosystems that support thousands of species, while the deep sea is home to organisms that survive in total darkness and under immense pressure. Earth is often described as a watery world, and for good reason. About 71% of the planet's surface is covered by water, the vast majority of which, approximately 97%, is held in its saltwater oceans. These oceans form the planet's most defining characteristic, shaping weather, climate, and life as we know it. From space, this massive expanse of water gives Earth its distinctive blue appearance, earning it the nickname the Blue Planet. The world's oceans are divided into 5 major ocean basins: the Arctic, Atlantic, Indian, Pacific, and Southern Oceans. While these oceans may appear distinct on a map, they are actually interconnected, forming one vast global ocean system. Each basin is essentially a deep depression in Earth's surface, filled with salt water and connected by complex circulation patterns that regulate the exchange of heat, nutrients, and life across the globe. The Arctic Ocean, the smallest and shallowest of the 5, is located around the North Pole. It is largely covered by sea ice throughout much of the year and plays a crucial role in regulating Earth's climate by reflecting sunlight back into space. The Atlantic Ocean, the second largest, stretches between the Americas and Europe and Africa. It is known for its powerful currents, such as the Gulf Stream, which play a vital role in climate regulation, particularly in the Northern Hemisphere. The Indian Ocean, bordered by Africa, Asia, Australia, and the Indian subcontinent, is the 3rd largest ocean basin. It is the warmest of all the oceans and has a significant impact on the monsoon systems that affect South and Southeast Asia. The Pacific Ocean is by far the largest and deepest of the ocean basins. Just how large is the Pacific? It's bigger than all of Earth's land masses combined. The Pacific reaches its greatest depth at the Mariana Trench, and it is also home to thousands of islands and some of the most biodiverse marine ecosystems on the planet. The Southern Ocean surrounds Antarctica and is the newest recognized ocean basin. Having been defined as a separate ocean by cartographers and scientists in the early 2000s, it plays a critical role in global ocean circulation, helping to drive the exchange of cold, dense water that circulates around the world. But that is not it. Beyond the vast open waters of the 5 ocean basins are smaller seas, which are usually partially enclosed by land and connected to the main ocean bodies. These seas can vary dramatically in size and depth, but they are all extensions of the major oceans. Some of the most well-known seas include the Mediterranean Sea, the Bering Sea, the Caribbean Sea, and the South China Sea. Though smaller, these seas often have significant ecological, economic, and cultural importance. For example, the Mediterranean Sea, nearly surrounded by southern Europe, North Africa, and the Middle East, has been a cradle of civilization for millennia, serving as a critical hub for trade, culture, and migration. It connects to the Atlantic Ocean via the Strait of Gibraltar, but its relatively enclosed nature means it has unique ecosystems and water circulation patterns. In contrast, the Bering Sea, located between Alaska and Russia, is part of the Pacific Ocean and is known for its rich marine life, including vast populations of fish, seabirds, and marine mammals. Its cold, nutrient-rich waters support some of the world's most important commercial fisheries. Though the world's oceans are divided into basins and seas, they are fundamentally one interconnected system, bound together by a vast network of currents, tides, and winds. These forces move water around the globe, creating the global conveyor belt of ocean circulation, which helps regulate Earth's climate. Warm waters from the tropics move toward the poles, while cold, dense water from the polar regions sinks and flows back toward the equator. This constant exchange of water helps balance temperatures across the planet, transporting heat from warmer areas to cooler ones and maintaining stable conditions that allow life to thrive. A key component of this global system is the thermo-Hallin circulation, sometimes referred to as the ocean's conveyor belt. Driven by differences in water density, which are influenced by temperature, thermo, and salinity, haline, this circulation connects all the world's ocean basins. Warm water from the equator flows northward, cools as it reaches the Arctic, and then sinks to the ocean floor due to its increased density. Then this cold, deep water slowly moves back toward the equator, completing the cycle. In addition to this, surface currents, like the Gulf Stream in the Atlantic and the Kuroshio Current in the Pacific, transport vast amounts of warm water across the planet's surface, influencing weather patterns and regional climates. For example, the Gulf Stream is responsible for the relatively mild climate experienced by countries in northern Europe, despite their high latitude. The interconnected nature of the world's oceans means that they play a vital role in regulating Earth's climate. The oceans absorb solar energy, with the equatorial regions acting as a heat reservoir. This stored heat is then redistributed across the globe via ocean currents. Without the moderating effect of the oceans, Earth's climate would be far more extreme, with hotter tropics and colder poles. Moreover, the oceans act as a massive carbon sink, absorbing nearly a quarter of all human-made carbon emissions. This helps slow the rate of climate change, though the increased levels of carbon dioxide are causing the oceans to become more acidic, threatening marine ecosystems. The ocean's ability to store and redistribute heat also helps to regulate weather patterns. The El Niño Southern Oscillation, ENSO for instance, is a phenomenon that originates in the Pacific Ocean and can drastically alter weather patterns around the globe, causing droughts, floods, and changes in storm intensity. These global connections demonstrate how closely linked the oceans are to the atmosphere and the rest of the planet's climate system. In essence, while we often refer to the world's oceans as distinct entities, they are part of a shared global ocean. Water from the Arctic can eventually find its way into the Pacific, and currents that begin near the coast of Africa can travel all the way to the shores of the Americas. This interconnectedness reminds us that what happens in one part of the ocean can have far-reaching consequences. Pollution, overfishing, and climate change in one region can affect ecosystems and human livelihoods thousands of miles away. The oceans are also crucial for biodiversity, home to countless species that depend on the delicate balance of marine ecosystems, from coral reefs in the warm, shallow waters to deep-sea creatures in the dark, cold depths. The variety of life that the ocean supports is staggering. It sustains the livelihoods of billions of people around the world, providing food, transportation routes, and opportunities for recreation. The interconnectedness of the oceans is a powerful reminder of how linked our planet is, from its ecosystems to its climate. Protecting and understanding the oceans is essential, not only for the survival of the creatures that live within them, but for humanity's future on this watery world. The oceans are truly vast, encompassing most of Earth's surface and holding the overwhelming majority of its water. Their immense scale and depth make them a defining feature of the planet, shaping everything from its climate to its ecosystems. With an average depth of about 12,000 feet, which is 3,700 meters, the oceans plunge far beyond what the human eye can see or comprehend, creating a realm of pressure and darkness where only the hardiest of life forms can survive. In total, the oceans contain an astounding 321 million cubic miles, which is 1.34 billion cubic kilometers of water, making them the largest reservoirs on Earth by far. While the oceans dominate Earth's water supply, only a small fraction of the planet's total water is available as fresh water. In fact, around 97% of Earth's water is salty, locked away in the vast expanses of the oceans. Of the remaining 3% of the planet's water, 2% is frozen in the form of glaciers, ice caps, and snow. This leaves just 1% of Earth's water available as free-moving freshwater, found in lakes, rivers, streams, and groundwater systems that support human life, agriculture, and most land-based ecosystems. This small percentage of freshwater is not distributed evenly around the world, with some regions experiencing abundant supplies, while others suffer from severe scarcity. Rivers like the Amazon or the Nile provide vital water sources for ecosystems and millions of people, yet when compared to the total volume of water held by the oceans, these rivers are mere drops in the global water cycle. Among the 5 ocean basins, the Pacific Ocean reigns supreme as the largest and deepest, spanning an immense 59 million square miles, which is 153 million square kilometers. The Pacific covers nearly half of the Earth's surface, making it larger than all of the land masses on Earth combined. This single ocean contains approximately 49% of all the salt water on the planet, holding more than all the other oceans put together. The Pacific's sheer size is staggering, stretching from the Arctic in the north to Antarctica in the south and touching the coastlines of Asia, Australia, the Americas, and numerous islands. The depth of the Pacific Ocean also sets it apart. At its deepest point, the Mariana Trench, the Pacific reaches down to 36,000 feet, which is 11,000 meters, an abyss so deep that it could swallow Mount Everest with room to spare. The Pacific's average depth is around 13,000 feet, which is 4,000 meters, making it not only the largest but also the deepest ocean on the planet. The Pacific's size and location give it an outsized role in global climate and weather systems. Its waters absorb solar energy from the sun and play a key part in distributing heat around the world through powerful currents like the Kuroshio and the North Pacific Gyre. This ocean also drives critical climate phenomena like El Niño and La Niña, which can cause dramatic shifts in weather patterns, affecting everything from rainfall to temperatures across the globe. Beyond its influence on climate, the Pacific is also one of the most biologically diverse regions on Earth. It is home to some of the planet's most vibrant ecosystems, including coral reefs, mangroves, and seagrass beds, which support thousands of species of marine life. The Pacific is also a vital resource for human populations, providing fisheries, shipping routes, and economic opportunities for the millions of people who live along its shores. The islands of the Pacific, such as those in Polynesia and Micronesia, are cultural and ecological treasures. Many of these islands are vulnerable to climate change and rising sea levels, making the Pacific a critical region for studying environmental impacts and implementing conservation efforts. The oceans are the driving force behind the global water cycle, a continuous process that moves water through different phases and ecosystems. As the largest reservoir of water, the oceans are responsible for the majority of evaporation that occurs on Earth. When the sun heats the ocean's surface, water evaporates and rises into the atmosphere, forming clouds. This water vapor eventually falls back to Earth as precipitation, feeding rivers, lakes, and aquifers. In this way, the oceans are directly connected to the freshwater systems that sustain human life and the global ecosystem. Because of the ocean's size and capacity to absorb and release heat, it plays a crucial role in regulating global temperatures. Water has a high heat capacity, meaning it can absorb large amounts of heat without significantly changing temperature. This ability helps the oceans act as a buffer, preventing extreme temperature fluctuations and maintaining a relatively stable climate across the planet. Without the moderating influence of the oceans, Earth would experience far more extreme weather patterns, with scorching heat during the day and freezing temperatures at night. Oceans are not just passive containers of water, they actively regulate the planet's climate. By absorbing carbon dioxide from the atmosphere, oceans serve as a massive carbon sink, helping to reduce the amount of CO2 in the air and mitigating the effects of climate change. However, as the oceans absorb more carbon dioxide, they become more acidic, a process known as ocean acidification, which threatens marine ecosystems, particularly organisms like corals, shellfish, and plankton, that rely on calcium carbonate to build their shells and skeletons. The circulation patterns of the oceans also play a crucial role in redistributing heat and nutrients. Warm water from the tropics is transported to higher latitudes, while cold, nutrient-rich water from the poles moves toward the equator. This circulation, driven by both wind and the Earth's rotation, creates complex current systems such as the Gulf Stream in the Atlantic and the Pacific's Kuroshio Current. These currents are critical for maintaining Earth's climate balance, influencing weather patterns, and supporting marine life by bringing nutrients to the surface. While the oceans contain the vast majority of Earth's water, the amount of accessible freshwater is surprisingly small. Only about 1% of Earth's total water is available as free-moving fresh water, found in rivers, lakes, and groundwater systems. This small percentage supports the entirety of human society and most terrestrial ecosystems, making freshwater one of Earth's most precious and limited resources. The 2% of water locked away in glaciers and ice caps also plays a vital role in regulating the planet's climate. As these ice sheets slowly melt due to rising global temperatures, they contribute to sea level rise, which poses a serious threat to coastal communities and ecosystems around the world. The loss of ice also reduces the planet's ability to reflect sunlight, further accelerating global warming. Earth's oceans, particularly the Pacific, are monumental in scale and crucial to the health of our planet. They dominate the global water cycle, regulate climate, and provide habitat for countless species, all while holding the vast majority of the planet's water. However, as much as the oceans give life, they are also vulnerable to the impacts of human activity. Climate change, pollution, and overfishing all threaten the delicate balance of these marine ecosystems. Understanding the sheer scale and importance of the oceans is the first step toward preserving them for future generations. The Earth's continents and oceans as we see them today are the product of billions of years of dynamic change. The familiar layout of land and water is dramatically different from how the planet looked in its early history, and it has been shaped by powerful geological forces that continue to reshape the surface of the Earth. To understand the evolution of Earth's oceans, we need to go back to a time when the planet was young and the conditions were vastly different from what we know today. When Earth first formed around 4.6 billion years ago, it was a molten ball of rock and metal, constantly bombarded by comets, asteroids, and other space debris. The intense heat generated by these impacts, combined with the decay of radioactive elements, kept the planet in a molten state for millions of years. During this period, Earth had no oceans, no atmosphere as we know it, and no conditions suitable for life. As the planet began to cool, volcanic activity played a crucial role in shaping Earth's surface and atmosphere. Volcanic eruptions released gases trapped deep within the planet, including water vapor, carbon dioxide, nitrogen, and other volatile compounds. These gases began to form a primitive atmosphere, with water vapor being a major component. Scientific evidence suggests that much of the water present in Earth's oceans today came from this early outgassing of water vapor from volcanic activity. Around 3.8 billion years ago, as Earth's surface continued to cool, conditions finally became stable enough for water vapor to condense into liquid. The planet's surface temperatures dropped to the point where water could no longer exist solely as vapor in the atmosphere, leading to the formation of clouds. Over time, these clouds condensed into massive rainstorms that lasted for millions of years. This rain fell onto the cooling surface of the Earth, collecting in the low-lying areas and gradually forming the first primitive oceans. The first oceans on Earth were vastly different from the ones we know today. They were likely shallow, acidic, and filled with dissolved minerals from the planet's surface. These early waters would have been constantly interacting with the still active volcanic landscape, absorbing gases like carbon dioxide, sulfur dioxide, and other compounds. Despite these harsh conditions, these primitive oceans played a critical role in shaping the future of Earth. They created an environment where life could begin to evolve. Scientists believe that life on Earth first emerged in these early oceans around 3.5 billion years ago. The oceans provided a relatively stable and protected environment where simple, single-celled organisms could thrive. Hydrothermal vents, which are fissures on the ocean floor that release heated water rich in minerals, may have been key to the origin of life. These vents provided a unique energy source for early life forms, allowing them to survive and evolve in an environment that was cut off from sunlight and the more volatile surface of the planet. While the early oceans were forming, the Earth's crust was also undergoing significant changes. The surface of the planet was gradually cooling and solidifying, forming the first continental plates. Over time, these plates began to move due to the process of plate tectonics, a fundamental force that continues to reshape Earth's surface. About 250 million years ago, all of Earth's land masses were joined together in a supercontinent called Pangaea, surrounded by a vast ocean known as Panthalassa. The movement of tectonic plates eventually caused Pangaea to split apart, breaking into smaller land masses that drifted across the surface of the Earth. This process of continental drift gave rise to the formation of today's oceans as the land masses slowly moved away from each other, creating the basins we now recognize as the Pacific, Atlantic, Indian, Arctic, and Southern Oceans. As these continents moved apart, new ocean basins were created, while seafloor spreading at mid-ocean ridges pushed the plates further apart. The Atlantic Ocean, for example, is relatively young in geological terms. It began to form when Pangaea broke apart during the Mesozoic era, around 200 million years ago. As the North American, South American, African, and Eurasian plates continued to drift, the Atlantic Ocean widened, and it continues to expand today at a rate of about 1 to 2 inches, which is 2.5 to 5 centimeters per year. While much of the water in Earth's oceans likely came from volcanic outgassing, there is also evidence suggesting that some of Earth's water may have originated from extraterrestrial sources. Early in Earth's history, the planet was bombarded by comets and asteroids, many of which contained significant amounts of water in the form of ice. These impacts may have contributed to Earth's water supply, delivering frozen water that melted and became part of the planet's early oceans. Some scientists believe that up to 30% of Earth's water could have come from these extraterrestrial sources, while others argue that the majority of the water was always part of Earth's mantle, released through volcanic activity over billions of years. Regardless of its origins, Earth's oceans have played a crucial role in shaping the planet's climate, geology, and the evolution of life. The ability of water to absorb and release heat has helped regulate the planet's temperature, making Earth habitable for a wide variety of life forms. The oceans are not static, they are dynamic systems that are constantly changing due to the movement of tectonic plates, sea level fluctuations, and climate variations. As continents continue to drift, new oceans will form, while others may shrink or close entirely. For example, the Red Sea is currently expanding due to the movement of the Arabian Plate and the African Plate. Over millions of years, this rift could become a fully developed ocean, much like the Atlantic. At the same time, the Pacific Ocean is gradually shrinking due to the subduction of oceanic plates beneath continental plates. The Pacific is ringed by subduction zones, areas where the oceanic crust is being pulled into the Earth's mantle and recycled. If these processes continue over the next tens of millions of years, the Pacific could eventually close, giving rise to new supercontinents and a completely different global oceanic layout. The story of Earth's oceans is a story of constant change, shaped by geological forces and climatic processes that have been in motion for billions of years. From the condensation of water vapor in the planet's early history to the breakup of supercontinents like Pangaea, the oceans we know today are the product of complex interactions between Earth's atmosphere, geology, and climate. Though the layout of the continents and oceans appears static from our human perspective, the Earth is always evolving. Tectonic activity, volcanism, and erosion are continuously altering the surface, creating new ocean basins, closing others, and changing the balance between land and sea. The vast expanses of water that cover the planet's surface, our oceans, remain one of the most powerful forces shaping the past, present, and future of Earth. Throughout Earth's history, the continents have undergone an extraordinary process of movement, drifting across the planet's surface, coming together to form massive supercontinents and then breaking apart again. This ongoing cycle of continental assembly and breakup is driven by the deep, unseen forces beneath the Earth's crust. These movements have shaped not only the geography of our planet, but also its climate, ecosystems, and the evolution of life. The most famous evidence of this phenomenon is the jigsaw fit of the coastlines of South America and Africa, which led early scientists to speculate that the continents were once joined together. If you examine a world map, you can see that the eastern coast of South America appears to fit neatly into the western coast of Africa, as if the two continents were once joined and then separated. This observation, first proposed by the German scientist Alfred Wegener in 1912, led to the theory of continental drift. Wegener suggested that the continents were once part of a supercontinent called Pangaea, which broke apart over millions of years. Wegener's theory was initially met with skepticism because he could not explain how the continents moved. It wasn't until later discoveries in geophysics and paleomagnetism that the mechanism for continental drift, plate tectonics, was understood. The discovery of mid-ocean ridges and the process of seafloor spreading provided the missing link, revealing that the continents move because they are carried along by the movement of tectonic plates. In addition to the jigsaw fit of the continents, paleontology provided strong evidence for continental drift. Similar fossils of ancient plants and animals have been found on continents that are now separated by vast oceans. For example, fossils of the extinct plant genus Glossopteris have been found in South America, Africa, India, and Antarctica, places that are now far apart but were once connected in the supercontinent Gondwana, which formed after Pangaea began to break apart. Another example is the fossil remains of the Mesosaurus, a small freshwater reptile found in both South America and southern Africa. Since Mesosaurus could not have swum across the Atlantic Ocean, the presence of its fossils on both continents provides clear evidence that these land masses were once connected. Such fossil records help to reconstruct the movements of ancient continents and confirm that they were once part of larger land masses that have since separated. The movement of continents is driven by the slow but powerful processes occurring deep within the Earth. Beneath the Earth's crust lies the mantle, a layer of semi-solid rock that moves very slowly over geological time. The Earth's lithosphere, which includes the crust and the upper part of the mantle, is broken into several tectonic plates that float on this slowly moving mantle. These plates are in constant motion, and their interactions at plate boundaries are responsible for many of the Earth's geological features, including mountain ranges, volcanoes, earthquakes, and the formation of ocean basins. At the boundaries between tectonic plates, volcanic activity and seafloor spreading occur. For example, along the mid-Atlantic ridge, magma rises from the mantle to the surface, creating new oceanic crust and pushing the plates apart. This process is what drives the expansion of the Atlantic Ocean. As the Eurasian and North American plates move away from each other on one side and the African and South American plates on the other, the Atlantic Ocean gradually grows wider by about 1 to 2 inches, 2 to 5 centimeters per year. At the same time, the Pacific Ocean is gradually shrinking due to the process of subduction, where the oceanic crust is being pushed beneath continental plates at the edges of the Pacific, particularly around the Ring of Fire, a region known for its intense volcanic activity and frequent earthquakes. Here, the Pacific plate is being subducted beneath the surrounding continental plates, causing the ocean to slowly contract over millions of years. The Red Sea, which lies between the African and Arabian plates, is also a site of tectonic activity. The African and Arabian plates are moving apart, creating a rift valley and expanding the Red Sea at a slow rate. Over millions of years, the Red Sea could become a larger ocean basin, much like how the Atlantic Ocean formed when the Americas drifted away from Europe and Africa. The movement of tectonic plates means that supercontinents like Pangaea have formed and broken apart several times over Earth's history in a process known as the supercontinent cycle. Before Pangaea, there were other supercontinents, such as Rodinia, which existed around 1.1 billion years ago. and Gondwana, which formed after Pangaea began to split. Pangaea itself began to break apart around 200 million years ago during the Mesozoic era. The initial rift that separated North America from Africa and Europe began the formation of the Atlantic Ocean, which has been expanding ever since. Over the course of hundreds of millions of years, continents continue to drift due to plate tectonics. And in the distant future, they may come together again to form a new supercontinent. Scientists predict that in 250 million years, Earth will likely experience the formation of another supercontinent, sometimes referred to as Pangaea Proxima or Pangaea Ultima. This new landmass will result from the ongoing movement of tectonic plates, with the Atlantic Ocean likely closing and the Pacific Ocean shrinking further. The land masses of today, which are slowly drifting apart, will eventually converge again, repeating the supercontinent cycle that has occurred multiple times throughout Earth's geological history. Today, the Atlantic Ocean continues to grow as the tectonic plates on either side move away from each other, while the Pacific Ocean is gradually shrinking as the Pacific Plate is subducted beneath surrounding plates. Though these movements are slow, on the order of a few centimeters per year, they have dramatic effects over millions of years. These processes not only shape the layout of Earth's continents and oceans, but also have profound effects on climate, ocean currents, and ecosystems. For example, the gradual widening of the Atlantic has influenced ocean circulation patterns that help regulate global temperatures. The formation of mountain ranges such as the Himalayas, the result of the collision between the Indian Plate and the Eurasian Plate, has also had a significant impact on climate and weather patterns in the surrounding regions. The movement of continents through plate tectonics is a slow but relentless force that has shaped Earth's surface for billions of years. From the formation of supercontinents like Pangaea to the expansion of oceans like the Atlantic, these processes continue to shape our planet today. Though the changes occur over vast timescales, their effects are monumental, influencing not just the geography of Earth, but also its climate, ecosystems, and the history of life. As the Atlantic Ocean grows and the Pacific Ocean and Red Sea shrink, we are witnessing just one phase in the ever-evolving story of our planet's surface. The movements we observe today are part of a long cycle that will continue to shape Earth for millions of years to come. The world's oceans and the global climate are deeply interconnected, creating a delicate balance that shapes the weather patterns, temperatures, and rainfall across the planet. This complex relationship arises from the interactions between the sun's heat, Earth's rotation, ocean currents, and wind patterns. The oceans act as a massive heat sink, absorbing, storing, and redistributing heat across the globe. In turn, the atmosphere responds to the ocean's movements and heat distribution, affecting weather systems and climate. The oceans absorb the majority of the sun's energy, particularly near the equator, where the sunlight is most direct. The equatorial waters act as vast solar collectors, soaking up heat. Water has a high specific heat capacity, meaning it can absorb and store large amounts of heat without experiencing a significant rise in temperature. This makes the oceans the primary regulators of Earth's temperature, capable of buffering large swings in heat that would otherwise lead to more extreme climates. Unlike land, which heats and cools quickly, the oceans absorb heat slowly and then release it gradually over time. This slow release of heat helps stabilize temperatures, particularly along coastal regions. Areas near oceans experience a moderating effect on their climate, leading to milder temperatures and more predictable weather patterns compared to regions that are far inland. This is why coastal areas typically have less extreme climates. Summers are cooler and winters are milder than in areas deep within continents. Just as the oceans are influenced by the sun's heat, wind patterns are also shaped by the energy coming from the sun. Wind is generated by differences in air pressure, which in turn are created by variations in temperature. As the sun heats the surface of the Earth, air near the surface warms up, becomes less dense, and rises, creating areas of low pressure. Cooler, denser air moves in to replace the rising warm air, creating wind. The prevailing winds that drive ocean currents are set in motion by the sun's energy and are further influenced by Earth's rotation. For instance, the trade winds blow consistently from east to west in the tropics, while the westerlies blow from west to east in the mid-latitudes. These wind patterns help push surface ocean currents, which transport heat across the globe and distribute it unevenly between the equator and the poles. The interaction between ocean currents and wind patterns plays a crucial role in shaping weather systems. For example, the warm waters of the Pacific Ocean can influence the formation of El Niño and La Niña events. During an El Niño event, the trade winds weaken, allowing warm water to pool in the eastern Pacific, which disrupts normal weather patterns. This leads to increased rainfall in some regions, like the western coast of South America, and droughts in others, like Southeast Asia and Australia. La Niña, on the other hand, is characterized by stronger trade winds and cooler waters in the Pacific, leading to opposite weather effects. The warmest waters on Earth are found in tropical regions, where the sun's rays strike the ocean surface most directly. As the ocean absorbs this heat, the warm water evaporates, creating moist air that rises into the atmosphere. This process of evaporation is most intense in the tropics, which is why rainfall is highest in tropical areas. As warm, moist air rises, it cools and condenses into clouds, releasing its moisture as rain. This is the foundation of the water cycle, where water evaporates from the oceans, forms clouds, and returns to the surface as precipitation. In tropical regions, the high rate of evaporation combined with the rising warm air creates frequent and intense rainfall. This is why areas like the Amazon Basin, Southeast Asia, and the tropical rainforests of Africa experience heavy rain throughout much of the year. In contrast, regions farther from the equator, where the ocean waters are cooler, experience less evaporation and therefore less rainfall. This is why areas at higher latitudes, particularly in desert regions, tend to have drier climates. The availability of water vapor in the atmosphere, and thus the likelihood of precipitation, is directly tied to the temperature of the oceans. The ocean's ability to store and slowly release heat has a profound impact on regional climates. Coastal areas, which are influenced by nearby bodies of water, tend to have a maritime climate, characterized by milder and more consistent temperatures compared to regions far inland, which experience a continental climate with more extreme temperature variations. For example, San Francisco benefits from the Pacific Ocean's moderating influence, which keeps the city's summers relatively cool and its winters mild. On the other hand, areas far from the ocean, such as the Great Plains of the United States or the Siberian interior, experience hot summers and cold winters, as there is no large body of water to buffer the temperature changes. The process by which the ocean moderates climate works through its ability to absorb solar energy during the day and slowly release that heat over time, particularly at night or during the winter months. The heat stored in the ocean prevents the air temperatures from dropping as quickly as they do over land, creating a more stable climate for regions located near coastlines. In essence, the oceans are the beating heart of Earth's climate system. They absorb, store, and distribute heat across the planet, shaping weather patterns, wind systems, and precipitation. Through complex interactions with the atmosphere and land, the oceans help maintain a balance that sustains life on Earth. Without the ocean's ability to regulate temperature and influence weather patterns, Earth's climate would be far more volatile and inhospitable. The impact of the oceans on global climate is not only about short-term weather patterns, but also about long-term climate trends. For example, the ocean's ability to absorb carbon dioxide plays a key role in mitigating the effects of climate change. However, as the planet warms, the ability of the ocean to absorb heat and carbon dioxide is being strained, leading to changes in ocean currents, sea level rise, and more frequent extreme weather events. In conclusion, the interaction between the oceans, atmosphere, and land creates a complex web of influences that govern the global climate. From regulating temperatures to driving wind patterns and controlling rainfall, the oceans are an essential part of the Earth's climate system, ensuring the planet remains habitable and stable over time. The ocean's power is most vividly demonstrated in the waves that roll across vast distances, eventually crashing onto shores with tremendous energy. These waves, generated by the winds that sweep across the surface of the ocean, are a constant reminder of the dynamic and relentless nature of the seas. Though they may look graceful from a distance, waves are a testament to the ocean's strength, capable of reshaping coastlines, influencing marine ecosystems, and even threatening human settlements during severe weather events. Waves begin as disturbances on the ocean surface, most commonly caused by wind. As the wind blows across the ocean, it transfers energy to the water, creating ripples that grow into larger waves over time. The size and strength of a wave depend on several factors, including the wind speed, the duration the wind blows, and the distance over which it blows, known as the fetch. Waves generated by storms, for example, can travel thousands of miles across the open ocean, gaining power and momentum as they move. Though the water within a wave does not travel forward in the same way that wind does, the energy from the wind is what propels the wave. The water molecules in a wave follow a circular motion, moving up and forward, then down and back as the wave passes. This motion continues until the wave approaches the shore, where it meets the seafloor. As a wave nears the coastline, its behavior changes dramatically. In the deep ocean, waves are smooth and relatively uniform, but as they approach shallow waters such as a reef or the shoreline, the base of the wave begins to interact with the seabed. This friction between the moving wave and the solid seafloor slows the wave down, causing the wave's energy to become concentrated at its crest. The water at the top of the wave continues moving faster than the water at the base, creating the steep, curling shape of a breaking wave. Off the south coast of New South Wales, Australia, for example, powerful waves regularly crash onto shallow reefs and beaches, particularly during storm surges or large swells. In these areas, waves that have traveled across the Southern Ocean arrive with significant force, shaped into mountain-like peaks as they reach the shallows. These waves grow in size and strength until they break, releasing their pent-up energy in a spectacular show of ocean power. The moment when a wave breaks is when its energy is finally released. The wave's steep crest topples forward, crashing into the shallows with immense force. In some cases, these waves can break with enough power to move large rocks, reshape coastlines, or even carve new landforms into the shore. The energy carried by waves has the potential to dramatically alter the landscape over time. The mechanics of a wave breaking are all about friction and drag. As the wave enters shallow water, the seabed interferes with the circular motion of the water particles within the wave. The deeper part of the wave slows down due to this drag, but the upper part continues to move forward at its original speed, creating instability. As the base slows and the crest moves ahead, the wave becomes top-heavy and eventually collapses. This process varies depending on the depth of the water, the steepness of the wave, and the shape of the seabed. Waves break differently depending on the underwater topography, resulting in different types of waves. A gradual slope will produce spilling waves, where the crest gently rolls over, while a steep slope will create plunging waves, where the wave curls over dramatically and crashes down with significant force, often forming the classic tube or barrel shape that surfers seek. In areas where waves approach a reef, the sudden change in depth causes them to break more violently. Reefs, with their shallow waters and sharp underwater structures, create friction that amplifies the intensity of waves, making these areas especially known for their large and powerful surf. The strength of waves also plays a crucial role in shaping coastal ecosystems. In places where waves frequently crash onto reefs or rocky coastlines, the impact of the water creates a unique environment that supports a variety of marine life. The constant motion of the waves oxygenates the water, providing a healthy habitat for organisms such as corals, seaweeds, and invertebrates that thrive in the rough, turbulent conditions near shore. Coral reefs, for example, are some of the most biodiverse ecosystems on the planet, and they depend on wave action to bring nutrients and oxygen to the reef. The physical structure of the reef acts as a barrier, absorbing the energy of incoming waves and protecting the coastline from erosion. At the same time, the constant water movement helps transport larvae, plankton, and other nutrients through the reef, ensuring the flow of life in the ecosystem. On the other hand, areas with calmer waters, such as mangrove forests and salt marshes, develop in more protected zones where wave energy is less intense. These ecosystems serve as important nurseries for marine species, where young fish and other organisms can grow without the threat of strong wave action. The balance between areas of strong wave impact and sheltered zones creates a mosaic of habitats that support a diverse range of species along coastlines. While waves are essential for maintaining coastal ecosystems, their strength can also pose a threat to human populations. During storms and tsunamis, the energy carried by waves can cause severe coastal erosion, destroy infrastructure, and flood low-lying areas. Storm-generated waves, especially during hurricanes and typhoons, have the potential to overwhelm coastal defenses, reshaping shorelines and leaving communities vulnerable to the destructive power of the ocean. However, the strength of ocean waves also offers a potential renewable energy resource. Wave energy technology seeks to harness the kinetic energy of waves and convert it into electricity. Coastal regions with consistent wave action, such as Australia, the United Kingdom, and the Pacific Northwest, have been exploring ways to tap into this sustainable energy source. By capturing the power of waves, we can transform the relentless energy of the ocean into a clean and reliable source of electricity, reducing our reliance on fossil fuels. The oceans are vast, covering about 70% of the Earth's surface, but what makes them even more extraordinary is the fact that they aren't just a flat, two-dimensional space. They're a three-dimensional environment, extending vertically from the sunlit surface waters all the way down to the dark, cold abyss of the ocean floor. This vertical structure of the ocean creates a wide range of habitats that are home to diverse marine organisms, each adapted to survive in dramatically different conditions. From the moment we gaze out at the sea, it's easy to imagine the ocean as a broad, flat surface stretching out to the horizon. However, beneath the waves lies a complex vertical world where organisms live in layers defined by sunlight, temperature, pressure, and nutrient availability. The ocean is not a uniform environment, and as you descend deeper into the water column, the conditions change dramatically. An organism living near the surface of the ocean will experience bright sunlight, warmer temperatures, and an abundance of oxygen and nutrients, allowing it to thrive in a relatively hospitable environment. In contrast, an organism living near the ocean floor, thousands of meters below the surface, faces pitch darkness, near-freezing temperatures, immense pressure, and a scarcity of food and nutrients. To make sense of this complexity, scientists divide the ocean into distinct zones based on the amount of sunlight each layer receives and the conditions that define each depth. Imagine plunging into the ocean, where light and life fade with each passing meter. The deeper you go, the more the water changes, as if you're passing through invisible layers of a vast, submerged world. These 5 ocean zones are like Earth's hidden kingdoms, each with its own rules, creatures, and secrets. The deeper you dive, the more alien life becomes, until it feels like you've left Earth altogether. Ready to explore? The ocean is divided into 5 major zones, each with its own unique characteristics. These zones are defined primarily by the amount of sunlight they receive, which influences temperature, pressure, and the types of organisms that can live there. As you descend from the surface into deeper waters, the ocean gradually becomes darker, colder, and less hospitable to life. But each zone supports organisms uniquely adapted to survive in its specific conditions. The epipelagic zone is the uppermost layer of the ocean, extending from the surface down to about 660 feet, which is 200 meters. This zone is also known as the photic zone, because it is the region where sunlight can penetrate the water. The sunlight in this zone allows photosynthesis to occur, making it the most productive part of the ocean and home to the majority of marine life. Phytoplankton, tiny plant-like organisms that float in the water, are the primary producers in the epipelagic zone. They convert sunlight into energy through photosynthesis, forming the base of the ocean's food web. Because of the abundance of sunlight, the epipelagic zone supports a rich diversity of life, including zooplankton, small fish, marine mammals, and large predators like sharks, tunas, and dolphins. Coral reefs, which are among the most biodiverse ecosystems on Earth, are also found in the shallow waters of the epipelagic zone, where sunlight is essential for the growth of coral and the symbiotic algae that live within them. In addition to sunlight, the epipelagic zone is rich in oxygen and nutrients. Ocean currents and winds stir the surface waters, bringing up nutrients from deeper layers through a process known as upwelling. This movement of nutrients supports the growth of plankton and fuels the entire marine food web. Below the epipelagic zone lies the mesopelagic zone, often called the twilight zone, which extends from 660 to 3,300 feet, which is 200 meters to 1,000 meters. In this zone, the sunlight fades to a dim, eerie glow, and temperatures drop significantly. Photosynthesis is no longer possible, and the organisms that live here must rely on food drifting down from the surface or on preying upon other organisms. Life in the mesopelagic zone has evolved fascinating adaptations to survive in these darker, colder waters. Many species, such as the lanternfish and dragonfish, have developed bioluminescence, the ability to produce light through chemical reactions in their bodies. This bioluminescence serves various purposes, such as attracting prey, camouflaging against predators, or communicating with other organisms. The mesopelagic zone is home to some of the largest migrations on Earth. Every night, millions of organisms, fish, squid, and zooplankton migrate from deeper waters to the surface to feed, then return to the depths by dawn. This movement, known as diel vertical migration, is driven by the need to avoid predators in the well-lit epipelagic zone during the day and take advantage of the food available at the surface at night. Descending further into the ocean, we reach the bathypelagic zone, often referred to as the midnight zone, which stretches from about 3,300 to 13,100 feet, which is 1,000 to 4,000 meters deep. At this depth, no sunlight penetrates, leaving the waters in total darkness. Temperatures here drop to just above freezing, around 35 degrees Fahrenheit to 39 degrees Fahrenheit, which is 2 degrees Celsius to 4 degrees Celsius, and the pressure is immense, about 5,800 pounds per square inch, more than 380 times the pressure at the surface. Despite the extreme conditions, life persists in the bathypelagic zone. The organisms that live here are adapted to the darkness, cold, and high pressure. Many of the creatures are slow-moving and have large, gaping mouths and expandable stomachs to take advantage of the scarce food that drifts down from the surface. One iconic inhabitant of this zone is the anglerfish, a fish with a bioluminescent lure that dangles from its head to attract unsuspecting prey in the darkness. The viperfish, with its long, fang-like teeth, is another deep-sea predator that uses light to hunt. Food in the bathypelagic zone is extremely limited, and most animals rely on marine snow, a constant shower of organic material composed of dead organisms, fecal matter, and other detritus that sinks from the surface. Some animals are also scavengers, feeding on the remains of dead animals that fall to the ocean floor, while others may venture up to the mesopelagic zone to hunt. Below the midnight zone lies the abyssopelagic zone, or simply the abyss, extending from 13,100 to 19,700 feet, which is 4,000 meters to 6,000 meters deep. The abyssal plains, some of the flattest and most desolate regions on Earth, dominate this zone. The conditions here are among the most extreme on the planet, with temperatures near freezing and pressures exceeding 11,000 pounds per square inch. Few organisms can survive in the abyss, but those that do have evolved remarkable adaptations to cope with the crushing pressure, lack of light, and scarcity of food. Many deep-sea creatures have soft, gelatinous bodies that can withstand the immense pressure, and some, like sea cucumbers and brittle stars, move slowly across the sea floor, feeding on detritus that falls from above. Bioluminescence is also common in the abyss, as light from organisms is the only form of illumination in this dark, cold environment. Some fish have hinged jaws that allow them to drag their mouths along the seafloor to capture food, while others, like the black swallower, can eat prey much larger than themselves due to their expandable stomachs. The deepest depths of the ocean is the hadalpelagic zone, which extends from 19,700 feet, which is 6,000 meters down to the bottom of ocean trenches, such as the Mariana Trench. This zone reaches depths of nearly 36,000 feet, which is 11,000 meters, making it the deepest part of the ocean and one of the least explored regions on Earth. The conditions in the hadalpelagic zone are even more extreme than in the abyss. Temperatures are near freezing, and the pressure is over 1,000 times that at sea level. Despite these seemingly inhospitable conditions, life persists, though it is sparse. Organisms such as isopods, amphipods, and sea cucumbers inhabit these depths, relying on the scarce nutrients that trickle down from above. How does life even exist in such an extreme environment? What could possibly survive under that kind of crushing weight? And yet, there is life. One of the most fascinating ecosystems in the hadalpelagic zone is found around hydrothermal vents and cold seeps. These are areas where superheated water rich in chemicals like hydrogen sulfide is expelled from the Earth's crust. In these otherwise barren environments, unique communities of life thrive, supported by chemosynthesis, a process in which bacteria convert the chemicals from the vents into energy. These bacteria, in turn, provide food for other organisms, such as giant tube worms, clams, and crabs, creating a vibrant ecosystem in one of the most extreme environments on the planet. The truth is, despite centuries of exploration, we've barely scratched the surface of what the oceans hold. Over 80% of the ocean remains unexplored. There are underwater landscapes, species, and phenomena that we've yet to encounter. What if the greatest discoveries still lie ahead? From the towering mid-ocean ridges to the crushing depths of the Mariana Trench, the oceans are Earth's final frontier. But they're more than just a mystery to be solved. They're our lifeline, responsible for everything from the air we breathe to the climate we live in. Remember how we started, looking at Earth from space, seeing that vast, endless blue. Now we know, beneath that blue lies a world more intricate, more dangerous, and more beautiful than we ever imagined. And while we've uncovered some of its mysteries, the journey to truly understand the oceans has only just begun. What will we discover next? What mysteries lie beneath the surface, waiting for us to uncover?